In physics, the Navier-Stokes equations, NavierStokes, named after Claude-Louis Navier and George Gabriel Stokes, describe the motion of viscous fluid substances. These balance equations arise from applying Newton's second law to fluid motion, together with the assumption that the stress in the fluid is the sum of a diffusing viscous term and a pressure term, hence describing viscous flow. The main difference between them and the simpler Euler equations for inviscid flow is that Navier-Stokes equations also in the Froude limit are not conservation equations, but rather a dissipative system, in the sense that they cannot be put into the quasi-linear homogeneous form. Navier-Stokes equations are useful because they describe the physics of many things of scientific and engineering interest. They may be used to model the weather, ocean currents, water flow in a pipe and airflow around a wing. The Navier-Stokes equations in their full and simplified forms help with the design of aircraft and cars, the study of blood flow, the design of power stations, the analysis of pollution, and many other things. Coupled with Maxwell's equations, they can be used to model and study magnetohydrodynamics. The Navier-Stokes equations are also of great interest in a purely mathematical sense. Somewhat surprisingly, given their wide range of practical uses, it has not yet been proven that in 3 dimensions solutions always exist, or that if they do exist, then they are smooth, i.e., they do not contain any singularity. These are called the Navier-Stokes existence and smoothness problems. The Clay Mathematics Institute has called this one of the 7 most important open problems in mathematics and has offered a $1 million prize for a solution or a counterexample. Flow velocity. The solution of the Navier-Stokes equations is a flow velocity. It is a field, since it is defined at every point in a region of space and an interval of time. Once the velocity field is calculated, other quantities of interest, such as pressure or temperature, may be found. This is different from what one normally sees in classical mechanics, where solutions are typically trajectories of position of a particle or deflection of a continuum. Studying velocity instead of position makes more sense for a fluid, however for visualization purposes one can compute various trajectories. General continuum equations. The Navier-Stokes momentum equation can be derived as a particular form of the Cauchy momentum equation. In an inertial frame of reference, the conservation form of the equations of continuum disambiguation needed motion is, whereas the density is the flow velocity, is the del operator, is the pressure, is the identity matrix, is the deviatoric stress tensor, which has order 2, represents body accelerations acting on the continuum. For example, gravity, inertial accelerations, electric field acceleration, and so on. The left side of the equation describes acceleration, and may be composed of time-dependent, convective, and hydrostatic effects. The right side of the equation is in effect a summation of body forces and divergence of deviatoric stress. In the Eulerian forms it is apparent that the assumption of no deviatoric stress brings Cauchy equations to the Euler equations. All non-relativistic balance equations, such as the Navier-Stokes equations, can be derived by beginning with the Cauchy equations and specifying the stress tensor through a constitutive relation. By expressing the shear tensor in terms of viscosity and fluid velocity, and assuming constant density and viscosity, the Cauchy equations will lead to the Navier-Stokes equations. The incompressible case is simpler than the compressible one, so for didactical purpose it should be presented before. However, the compressible case is the most general framework of Navier-Stokes equations, so where not specified. Navier-Stokes equations are intended to be compressible Navier-Stokes equations. Convective acceleration, a significant feature of Cauchy equation and consequently all other continuum equations, is the presence of convective acceleration, the effective time-independent acceleration of a flow with respect to space. While individual fluid particles indeed experience time-dependent acceleration, the convective acceleration of the flow field is a spatial effect. One example being fluid speeding up in a nozzle. Incompressible flow. The incompressible momentum Navier-Stokes equation results from the following assumptions on the Cauchy stress tensor. The stress is Galilean invariant. It does not depend directly on the flow velocity, but only on spatial derivatives of the flow velocity. So the stress variable is the tensor gradient. The fluid is assumed to be isotropic, as with gases and simple liquids, and consequently is an isotropic tensor. Furthermore, since the deviatoric stress tensor can be expressed in terms of the dynamic viscosity μ, where I is the identity tensor, and is the rate of strain tensor, so this decomposition can be explicited as dynamic viscosity μ need not be constant. In incompressible flows it can depend on density and on pressure. Any equation expliciting one of these transport coefficient in the conservative variables is called an equation of state. The divergence of the deviatoric stress is given by incompressibility rules out density and pressure waves like sound or shock waves. So this simplification is not useful if these phenomena are of interest. For incompressible flows the following identity holds, where W is the specific thermodynamic work, the internal source term. Then the incompressible Navier-Stokes equations are best visualized by dividing for the density, velocity profile, for the direction. Simplify Navier-Stokes equation, integrate twice to find velocity profile with boundary conditions. From this equation, sub in your two boundary conditions to get two equations, add and solve for B, substitute and solve for A. Finally you get the velocity profile in tensor notation, where nu equals mu, rho 0 is the kinematic viscosity. It is well worth observing the meaning of each term. The higher order term, namely the shear stress divergence tau, has simply reduced to the vector Laplacian term mu 2u. This Laplacian term can be interpreted as the difference between a velocity at a point and the mean velocity in a small surrounding volume. This implies that, for a Newtonian fluid, viscosity operates as a diffusion of momentum, in much the same way as the heat conduction. In fact, neglecting the convection term, incompressible Navier-Stokes equations lead to a vector diffusion equation. But in general the convection term is present, so incompressible Navier-Stokes equations belong to the class of convection diffusion equations. In the usual case of an external field being a conservative field, by defining the hydraulic head, one can finally condense the whole source in one term, arriving to the incompressible Navier-Stokes equation with conservative external field. The incompressible Navier-Stokes equations with conservative external field is the fundamental equation of hydraulics. The domain for these equations is commonly a 3 or less Euclidean space, for which an orthogonal coordinate reference frame is usually set to explicit the system of scalar partial derivative equations to be solved. In 3D orthogonal coordinate systems are 3. Cartesian, cylindrical, and spherical. Expressing the Navier-Stokes vector equation in Cartesian coordinates is quite straightforward and not much influenced by the number of dimensions of the Euclidean space employed. And this is the case also for the first-order terms also in non-Cartesian orthogonal coordinate systems. But for the higher-order terms some tensor calculus is required for deducing an expression in non-Cartesian orthogonal coordinate systems. The incompressible Navier-Stokes equation is composite, the sum of two orthogonal equations, where πs and πi are solenoidal and rotational projection operators satisfying πs plus πi equals 1 and phi are the non-conservative and conservative parts of the body force. This result follows from the Helmholtz theorem. The first equation is a pressureless governing equation for the velocity, while the second equation for the pressure is a functional of the velocity and is related to the pressure Poisson equation. The explicit functional form of the projection operator in 3D is found from the Helmholtz theorem. with a similar structure in 2D. Thus, the governing equation is an integro-differential equation similar to Coulomb and Biot-Savart law, not convenient for numerical computation. An equivalent weak or variational form of the equation, proved to produce the same velocity solution as the NavierStokes equation, is given by, for divergence-free test functions W satisfying appropriate boundary conditions. Here, the projections are accomplished by the orthogonality of the solenoidal and the rotational function spaces. The discrete form of this is eminently suited to finite element computation of divergence-free flow, as we shall see in the next section. There we will be able to address the question, how does one specify pressure-driven problems with a pressureless governing equation? The absence of pressure forces from the governing velocity equation demonstrates that the equation is not a dynamic one, but rather a kinematic equation where the divergence-free condition serves the role of a conservation equation. This all would seem to refute the frequent statements that the incompressible pressure enforces the divergence-free condition. Discrete velocity with partitioning of the problem domain and defining basis functions on the partitioned domain. The discrete form of the governing equation is, it is desirable to choose basis functions which reflect the essential feature of incompressible flow. The elements must be divergence-free. While the velocity is the variable of interest, the existence of the stream function or vector potential is necessary by the Helmholtz theorem. Further, to determine fluid flow in the absence of a pressure gradient, one can specify the difference of stream function values across a 2D channel, or the line integral of the tangential component of the vector potential around the channel in 3D, the flow being given by Stokes' theorem. Discussion will be restricted to 2D in the following. We further restrict discussion to continuous Hermite finite elements which have at least first derivative degrees of freedom. With this, one can draw a large number of candidate triangular and rectangular elements from the plate bending literature. These elements have derivatives as components of the gradient. In 2D, the gradient and curl of a scalar are clearly orthogonal, given by the expressions, adopting continuous plate bending elements, interchanging the derivative degrees of freedom and changing the sign of the appropriate one gives many families of stream function elements. Taking the curl of the scalar stream function elements gives divergence-free velocity elements. The requirement that the stream function elements be continuous assures that the normal component of the velocity is continuous across element interfaces. All that is necessary for vanishing divergence on these interfaces. Boundary conditions are simple to apply. The stream function is constant on no-flow surfaces, with no slip velocity conditions on surfaces. Stream function differences across open channels determine the flow. No boundary conditions are necessary on open boundaries, though consistent values may be used with some problems. These are all Dirichlet conditions. The algebraic equations to be solved are simple to set up, but of course are nonlinear, requiring iteration of the linearized equations. Similar considerations apply to 3 dimensions, but extension from 2D is not immediate because of the vector nature of the potential, and there exists no simple relation between the gradient and the curl as was the case in 2D. Pressure recovery. Recovering pressure from the velocity field is easy. The discrete weak equation for the pressure gradient is, where the test weight functions are rotational. Any conforming scalar finite element may be used. However, the pressure gradient field may also be of interest. In this case one can use scalar Hermite elements for the pressure. For the test weight functions g, one would choose the irrotational vector elements obtained from the gradient of the pressure element. Compressible flow. The NavierStokes equations result from the following assumptions on the stress tensor. The stress is Galilean invariant. It does not depend directly on the flow velocity, but only on spatial derivatives of the flow velocity. So the stress variable is the tensor gradient u. The stress is linear in this variable. sigma equals c, where c is the fourth-order tensor representing the constant of proportionality, called the viscosity or elasticity tensor, and is the double dot product. The fluid is assumed to be isotropic, as with gases and simple liquids, and consequently is an isotropic tensor. Furthermore, since the stress tensor is symmetric, by Helmholtz decomposition it can be expressed in terms of two scalar λ parameters, the bulk viscosity lambda and the dynamic viscosity mu, as it is usual in linear elasticity, where I is the identity tensor, epsilon 1/2 u plus 1/2 t is the rate of strain tensor and u is the rate of expansion of the flow. So this decomposition can be explicited as, since the trace of the rate of strain tensor in 3 dimensions is the trace of the stress tensor in 3 dimensions becomes so by alternatively decomposing the stress tensors into isotropic and deviatoric parts, as usual in fluid dynamics. Introducing the second viscosity zeta, we arrive to the linear constitutive equation in the form usually employed in thermal hydraulics. Both bulk viscosity lambda and dynamic viscosity mu need not be constant. In general, they depend on density, on each other, and in compressible flows also on temperature. Any equation expliciting one of these transport coefficient in the conservation variables is called an equation of state. By computing the divergence of the stress tensor, since the divergence of tensor u is 2u and the divergence of tensor t is, one finally arrives to the compressible Navier-Stokes momentum equation. Bulk viscosity is assumed to be constant, otherwise it should not be taken out of the last derivative. The effect of the volume viscosity zeta is that the mechanical pressure is not equivalent to the thermodynamic pressure. This difference is usually neglected, sometimes by explicitly assuming zeta equals 0, but it could have an impact in sound absorption and attenuation and shock waves. See. For the special case of an incompressible flow, the pressure constrains the flow so that the volume of fluid elements is constant. Isochoric flow resulting in a solenoidal velocity field with u equals 0. Other equations. The Navier-Stokes equations are strictly a statement of the balance of momentum. To fully describe fluid flow, more information is needed, how much depending on the assumptions made. This additional information may include boundary data, conservation of mass, balance of energy, and/or an equation of state. Continuity equation. Regardless of the flow assumptions, a statement of the conservation of mass is generally necessary. This is achieved through the mass continuity equation, given in its most general form as, or, using the substantive derivative. In the example below we can assume to have a Newtonian fluid as well as having and both be constant. Recall that mass continuity is simply the summation of the rate of mass in and the rate of mass out. Rate of mass accumulated equals rate of mass in, rate of mass out. Since there is no change in density over time, we have recall that is a constant, thus proving the divergence theorem above. Stream function for 2D equations. Taking the curl of the Navier-Stokes equation results in the elimination of pressure. This is especially easy to see if 2D Cartesian flow is assumed, where the equations reduce to differentiating the first with respect to y, the second with respect to x, and subtracting the resulting equations will eliminate pressure and any conservative force. Defining the stream function through results in mass continuity being unconditionally satisfied, and then incompressible Newtonian 2D momentum and mass conservation condense into one equation, where is the B-harmonic operator and is the kinematic viscosity. We can also express this compactly using the Jacobian determinant. This single equation together with appropriate boundary conditions describes 2D fluid flow, taking only kinematic viscosity as a parameter. Note that the equation for creeping flow results when the left side is assumed 0. In axisymmetric flow, another stream function formulation, called the Stokes stream function, can be used to describe the velocity components of an incompressible flow with one scalar function. The incompressible Navier-Stokes equation is a differential algebraic equation, having the inconvenient feature that there is no explicit mechanism for advancing the pressure in time. Consequently, much effort has been expended to eliminate the pressure from all or part of the computational process. The stream function formulation eliminates the pressure but only in 2 dimensions and at the expense of introducing higher derivatives and elimination of the velocity, which is the primary variable of interest.